Hello and welcome everyone. Good morning or good evening, wherever you are. My name is Gal Greenberg, and I have the pleasure to moderate this webinar on eco-reuse, chloramine-free water reuse solution. The webinar will be presented by Lior Eshed from IDE Technologies. Lior Eshed is graduate of the Technion, the Israeli Institute of Technology, with Bachelor of Science and Master of Science in Environmental Engineering. Lior has been with IDE Technology since 2015 as a process engineer at the R&D team, focusing on reuse technology. He has been actively involved with some of IDE's largest RO desalination and water reuse projects, as well as industrial water treatment ones. Lior has significant expertise in the field of membrane technology, sludge treatment, log removal, and more. He is experienced in the process design and process engineering of desalination units for a wide range of water types, including seawater, industrial, and wastewater. Lior holds various patents in this field. Before we continue, I would just like to note that we will be taking questions and will be answering them at the end of the presentations. If you would like to submit a question, please do so by using the Ask a Question button just below. And now, Lior, over to you.
All right, so thank you all for joining this IDE's webinar on water reuse. My name is Lior Eshed. I am IDE's product manager in the field of water reuse. So let's start with a quick introduction about IDE. So IDE is a bit more than 50 years old now, established in 1965 as technology pioneers in the field of desalination, both in industrial water and wastewater reuse. With large and growing patent portfolios and offices worldwide, unrivaled experience with more than 400 installations to date in over 40 countries, with specific focus on mega plants. A few examples for such installations, large installations, would be Sorek desalination plant, which is the world's largest seawater RO desalination plant in Israel, 165 MGD. Another example would be in Tianjin, China, in which there is the largest desalination plant in China. In Reliance, India, the largest desalination plant in India with 106 MGD. And last would be Carlsbad in the United States of America, which is the largest desalination plant in the Western Hemisphere with 54 MGD. So a quick introduction to those of you who are not well familiar with the field of water reuse. Just a few words about why water reuse to begin with. So needless to say, there is a growing demand for potable water in water scarcity conditions, with a lot of examples such as in California, Texas, Australia, South Africa. When compared between water reuse, which means taking wastewater, secondary effluent or tertiary effluent, and turning them into potable water that could be used either as direct potable reuse or indirect potable reuse, one of the biggest advantages of using secondary or tertiary effluent would be its low TDS of the source water. For instance, compared to seawater RO, that means that you can operate the process in low pressure, thus saving energy, meaning that you'll have a cost-effective process. Wastewater are everywhere. That means that you have abundant sources of water. Water treatment plants, wastewater treatment plants are spread all over. There is low environmental impact. You do not need to build special and expensive intakes, such as in the case of seawater. And it's a proven technology with long reference list, big installations, such as the one in Orange County in the United States, and many more. Another thing would be the strict and known regulations, such as the Title 22 in California and other places as well. So the regulation is known and the technology is there. So all the good benefits to use this technology. So let's start with a little overview of the conventional water reuse process scheme, also called fully advanced treatment or FAT. So normally you would start with chloramination. That is to react between chlorine and ammonia. Either the ammonia is already present in the secondary effluent, or you need to dose it specifically. And that is in order to keep the membranes, the MF and after that the reverse osmosis membranes clean as much as possible from biofouling. So chloramines are used in order to control biofouling. So the next step would be either ultrafiltration or microfiltration. This step is there in order to remove suspended solids, not dissolved organic matter. Next step would be the heart of the process, which is the reverse osmosis membrane, which removes salts and dissolved organic matter, viruses, and so on. Special focus on pathogens. And the last process would normally be the UVAOP. UVAOP stands for ultraviolet advanced oxidation process. And this step is there in order to remove residual organic matter that may have passed through the RO. Now, as you see, the first step is chloramination. Now, chloramination is a must in order to keep the membranes clean of biofouling, or at least under controlled conditions, but it has some drawbacks. So first of all, chloramination, you need to dose the hypochlorite, and sometimes you also need to dose ammonia, if not naturally present in the water, so that means that you'll have expenses. The other thing would be that those chemicals may damage, oxidize the membrane if not dosed carefully, thus creating more complex monitoring and control system. Most importantly, chloramines may promote NDMA formation, and I'll elaborate about that a bit more. NDMA is a semi-volatile organic molecule that is toxic and a suspected carcinogen. And chloramines were also found to reduce UVT, therefore requiring more energy, something between 30 to 40% more in the subsequent UVAOP. That is because the UVT value, UVT basically means how transparent the water is, so that determines how efficient your UVAOP system would be. The higher the UVT, the more transparent the water is, the better the energy emitted by the UV lamp can pass through the water. So if you dose chloramines, you will lower your UVT value and therefore reduce your efficiency of the UVAOP process. When you look about log removal means each log removal means 90% removal of either bacteria, protozoa, or viruses. So if you talk about 2 log removal, you mean 99% and so on. Title 22, which is the Californian regulation, which is pretty much the leading regulation in the world today, demands that your process will remove 10 log of bacteria, 10 log of protozoa, and 12 log of viruses. And that should be done with at least 3 processes, such as the MF or UF, RO, and UVAOP. In addition, there is a requirement to remove at least half a log of 1,4-dioxane. 1,4-dioxane is an organic contaminant. So you see that this fully advanced treatment process stands very well with the demand to remove 10 log of bacteria as well as 10 log of protozoa. However, in viruses, this process produces only 8 log removal, but there is a requirement for 12. So that means that viruses require an additional 4 log removal, which may be done through chlorination or underground travel time. You get 1 log removal for each month of underground travel time. Now let's go back a little bit about the NDMA, this semi-volatile organic molecule that is created when hypochlorite comes in contact with organic matter. So NDMA is an organic contaminant. It's toxic to liver and other organs. It's suspected human carcinogen, and maximum allowed in water is 10 nanograms per liter. So in order to avoid the formation of NDMA, one must not dose chloramine to the system. However, you still need to make sure that your membrane is clean of biofouling. So how can you make sure that your system stays working in good working conditions without dosing chloramine? This brings us to the eco-reuse process. So what you see here is the conventional fully advanced treatment that I presented earlier, but with a few changes. So first thing would be eliminate the chloramine dosage. That means no NDMA formation, no risk of membrane oxidation. How do you control the biofouling then? So what we do, we use preventive maintenance approach. That means that instead of using chloramine, we're using a technology called direct osmosis high salinity. That is the injection of So that means the injection of a short pulse of concentrated salt, which changes the balance on the membrane between the gauge pressure that is done or operated by the high pressure pump and the osmotic pressure, therefore creating backwash of the membrane. And I will elaborate about that in a few seconds. The other thing that we do is use conservation process, which means flushing of the membrane with permeate water. And by doing so, we remove any protocrystals that can produce scaling on the membranes. We do this preventive maintenance approach a few times a day instead of dosing chloramines. So that means that your membrane is clean all the time. There is no buildup of biofouling or scaling, and you keep your membranes intact and in good shape without the dosage of those risky chemicals. The other benefit of not dosing chloramines is that there is no UVT reduction. That means that your UV AOP process will be more efficient by about 30 to 40%, also in CAPEX and in OPEX. The other benefits of using this preventive maintenance approach is that you'll have longer intervals between CIPs on the RO, and your life expectancy of the membrane may be longer. So the DOHS, as I said, is the backwash, creates backwash movement of the membrane surface by forward osmosis. There is a rapid increase in cross-flow velocity since there is permeate movement towards the feed brine side. And the other benefit is that there is bacteria dehydration due to osmotic shock. That is because there is introduction of highly concentrated saline solution onto the membrane surface, and those bacteria are suddenly exposed to very high saline concentrations that cause them to shrink on the membrane, therefore being inactivated, but they do not go through lysis process. That means that their organic matter does not go outside of their cell and do not contain or contaminate the membrane. The other process that I mentioned is called conservation, which is the periodic flushing of the membrane with permeate to cause scaling dissolution. So how does the DOHS or direct osmosis high salinity work? So in normal operation, there is feed to brine movement of the membrane, and in reverse osmosis, you have the feed pump that pressures the water to go through the membrane from the feed side towards the permeate side. When we inject this highly concentrated saline solution, this balance between the osmotic pressure and the gauge pressure created by the pump is converted, and now there is movement of permeate water from the permeate side to the feed side, creating backwash of the membrane. As this pulse moves along the pressure vessel, it diminishes because there is more and more water flowing from the permeate side to the feed side. Therefore, the amplitude of this concentrated salt solution becomes lower and wider. However, since there is more and more movement of permeate water from the permeate side to the feed side, there is an increasing shear force that removes also organic matter from the membrane. This sketch also shows what's happening here. You see that the highly concentrated saline pulse is in the middle of the pressure vessel, but on the first element and the last element, the membrane does not really know that this pulse is there, and it continues to operate in standard reverse osmosis mode. The permeate that is being made in those membranes, in those elements, pass inside the pressure vessel towards the membrane that is currently being flushed by this concentrated salt solution, and go from the permeate side to the feed side, thereby lifting whatever residual organic matter you had on the membrane. So the outcome of this is a backflow of the membrane, backwash of the membrane, as well as shear force on the membrane that also helps in removing organic matter. And the other effect would be the dehydration of bacteria. When we look at the brine after or during this DOHS process, you can see an increase in the brine conductivity, which is of course the result of this concentrated saline solution that passes through the pressure vessels and exits it. But the other thing that you see is, in parallel to the increase in brine conductivity, you see brine turbidity rising up, which basically proves that this DOHS process removed organic matter and fouling that was on the membrane between those DOHS cycles. So this shows the efficiency of this DOHS process. Now I will go to the second part of this presentation, showing some results of this technology. So we had this technology operating in Israel in our R&D site in Herzliya wastewater treatment plant. And the other facility would be Pismo Beach in California, in which there is a demonstration site that shows this technology. Actually, tomorrow is going to be the ribbon cutting of this facility. So this project is a collaboration between the city of Pismo Beach, which is hosting this demonstration facility, WSC, and Carollo, which give all the technical and the analytical support, and IDE, which provided the technology and the facility itself. Some technical details about this facility. So it is currently operating in this eco-reuse phase, meaning no chloramine dosage, using all those preventive maintenance approach that I presented earlier. The next phase will be in standard fully advanced treatment process that will serve as a benchmark to compare those two technologies. So now we're operating in the eco-reuse, and the next step will be to operate in the standard fully advanced treatment process. The MF that is present there is POS MF containing 4 UNA elements. The RO is in the first stage a single 8-inch membrane, a single 8-inch pressure vessel with 7 elements of Dow Eco Pro 400, and 2 pressure vessels in the second phase of 4-inch with Dow BW30 XFRLE 4040 membranes. The RO operated in recovery of 75 and now currently in 80% recovery. 2 stages of the RO. The first stage operates in flux of 11 to 13.4 gallon per foot per day and 10 to 11.2 gallon per foot per day on the second stage. The permeate flow rate would be 30 to 35 gallon per minute. And the UV AOP is by Evogua, which is also quite a unique system because it is chemical free. There is no injection of hydrogen peroxide or chlorine. The free radicals are being created on site there without any dosage of chemicals. Now let's go a little bit into some of the results. So this slide shows the specific flux in this plant. So you see that in the first 2 weeks there was compaction. This is normal when you introduce new membranes to the system. In the first 2-3 weeks, there is compaction of the membrane, resulting in a decrease of about 20% in the specific flux. And after that, you see that the specific flux remained quite stable, but a little bit decrease in performance during April, since there was a problem in the dosing of the acid. After fixing that, it recovered a little bit, but altogether quite stable. When we compare this performance to Orange County water facility, for instance, water use facility, you see that the first stage in Pismo Beach operates in specific flux of about 0.12 to 0.13 gallon per foot per day per PSI. Compared to Orange County, it is about 20% higher or a bit more. Second stage would be about the same, around 0.09, 0.1 gallon per foot per PSI. So altogether, the first stage operates in about 20% higher specific flux, and second stage about the same. When looking at the normalized differential pressure in the membrane, then the differential pressure is an indicator of fouling buildup or scaling buildup on the membrane. You see that during the first 1.5-2 months, the DP was very stable. In April, there was about 10% increase, again, as a result of lack of acid dosage, but after that, it stabilized with about 14 psi in the first stage and about 17 psi in the second stage. Again, when compared to Orange County, this would be lower figures. In the first stage, it would be about 30% lower. The second stage would be about the same. When we look at the conservation of the membrane, that's the second process that we do in order to keep the membrane clean, you see a very interesting approach. The conservation, that is the flushing of the membrane with permeate water, when we do it in a time-dependent way, meaning that you operate your system for a certain amount of time, and then you track the turbidity that leaves the system, meaning how much turbidity was removed from the RO, you see a classic time-dependent result. Conservation takes about 20 minutes. So when we look at the turbidity profile of the water that leaves the system in the brine stream, you see that after a longer period of time, the turbidity is higher, and the area below the graph, meaning how much turbidity was actually removed from the membrane, is very much dependent on the time between those conservation cycles. So if you operate the system for 6 hours between those conservation cycles, you see that there is more matter removed from the membrane, whereas if you do these conservation cycles in short time, that means that there is less stuff to remove, and therefore this is the lower profile that you see there. So that means that the conservation is indeed an effective process to keep the membrane clean. There is direct correlation between the operation duration and turbidity removed by this conservation process. When we look at the performance of the MF, that is the pretreatment to the RO, we see that there is pretty much standard TMP, stable TMP with constant flux. The flux is the 33 GFD. I would say a little bit high flux when compared to other facilities. The TMP was very stable, but on the last part there, when you see this increase in the TMP, that was the result of not feeding ferric. We use ferric as a coagulant in this MF system in order to help the MF operate with this coagulation. So what happened here was that there was no ferric dosage, and we see this immediate impact on the MF performance. When we reintroduced ferric into the system, the TMP was very stable, and specific flux returned to normal. When we compare the flux, that is 33 gallons per foot per day, to the one, for instance, in Orange County, you see that in Orange County the operation is around 20 gallons per foot per day, so the MF performs really nicely there. We started with the daily cleaning of the membrane. Again, I remind you there is no chloramine fed in there, so we started with daily chemical cleaning using only hypochlorite. But then we saw that the performance was very stable and clean, so we started to do this for only every 2 days instead of a single day. And there we see this, there is no ferric dosage, we see this immediate impact on the performance. When we look at the specific flux was also quite stable. Again, when there was no ferric dosage, we saw this immediate impact on the specific flux, but upon returning to the coagulation being fed as usual, it returned to its original point. The filtrate quality was very good. SDI was all the time below 2, and in spite of fluctuations in the feed turbidity, you see that the filtrate turbidity is very, very stable, producing high quality filtrate. Another important factor is the MF integrity testing. So this graph shows that the membrane kept its integrity. It kept the same pressures all the time, showing that there was no harm of the membrane in spite of no chloramine dosage. So the MF retained its integrity during the time. The same, by the way, was also with the RO. As done by numerous testing that was done on the membrane, the RO kept its log removal as always. So to conclude the performance of this pilot that has now been operated for 3 months, it showed stable performance. The preventive maintenance mechanism was effective. Specific flux was high. UVT was almost 100%, meaning that the UV AOP was operating very well with energy savings. The MF and the RO membranes kept intact, so their integrity was not harmed. All this chloramine-free, without any NDMA formation. When we look at the process in general, you see that the eco-reuse process provides a safer product due to the elimination of chloramine dosage, no NDMA, reduced chemical consumption. You may get longer CIP intervals during your operation because your membrane is kept clean. There is lower energy consumption because there is less frequent membrane cleanings. Higher UVT means that you'll be able to operate the UV AOP at about 30% less energy, also a smaller system, so you'll also get savings on the capex. And of course, reduced carbon footprint due to higher energy efficiency process. So with that, I'll conclude. I would like to thank everyone for joining, and I'll be happy to take any questions.
Thank you, Lior. And now we'll move to your questions. The first question is, what is the maximum recovery you can reach with this technology?
So the technology in this system would be similar as you'd always get in any water reuse facility. Normally with a 2-stage process, you will work around 75–80%. You can even reach a bit more than that. You may reach 85% and even more using 3 stages. So this eco-reuse technology is not any different than the standard fully advanced treatment when referring to recovery.
The next question: does the cleaning techniques you mentioned affect the quality of the product?
Yes, that's a perfect question. So the quality of the product remains the same as you'll always get. So when you talk about DOHS, you basically say that you have a backwash of the membrane, but the water that passes through the membranes is the same because you do not change the membrane itself. So whatever permeate quality you may get in standard operation, you will get the same quality with the same technique. Again, you will not get any NDMA formation because there is no chloramine dosage. So when you refer to that, you'll have a higher quality than normal.
Next question. Can the eco-reuse process easily be implemented into an existing RO system?
Right, so that's also a good question. So yes, retrofit can be done. Basically, you stop dosing chloramine and you install the DOHS system as well as the conservation system. That's quite an easy fix. What you basically need to do is add a dosing system of hypersaline solution, which is easily done. Also add flushing to the system, which is also very easy to do. So retrofit can surely be done, and I think that you also get significant savings on your UVT as well as savings on chemicals. So to conclude, retrofit for sure can be done.
Okay, and last questions. Which is the NaCl concentration you are injecting and flow rate of injection?
Yes. So the hypersaline concentration in the tank, what is being fed is saturated saline solution. I would say something between 22 to 24%, and it is being injected in a ratio of about 1 to 3. So altogether, in your feed to the RO, you'll get around 8% of saline concentration. And what was the other question?
That's it. You answered the two questions.
Okay.
Concentration and flow.
Flow, right. So the flow rate is about 1 to 2 then. Okay. So thank you, everyone. Thank you all for joining this presentation. And if there is any other questions, please email me. I'll be happy to answer. That would be lior@ide-tech.com. Thank you very much.
Thank you, everyone. Recording of this webinar will be available on our web in the coming days.